this.
Hi everyone, my name is Erwin Reisner from Cambridge University. It's a real pleasure to be here and to chair this session. Before I go into it, I'd really like to thank Seb, Alex, Glenda and the whole Solar Fuels Network team for doing a great job of bringing us together and organizing this virtual event. And of course, also all the speakers and poster presenters so far. I think it still shows even in the pandemic times, we still can come together electronically and have some really inspiring discussions. This being said, of course, I still hope that the next annual event can be in person to bring also especially the students back into the same room and discuss or maybe have some interactions there. So the purpose of this session is really to talk also to the general public, not only the solar fuels experts, and implying that solar fuels now is under some pressure to get real. So we're really looking forward to see some implementation, hopefully in the not too distant future. And we are very lucky that we have 3 brilliant speakers in this session who talk about really roadmaps that are being in development, large initiatives, and also already some ongoing activities on a significant scale to produce fuels at least sustainably. When I say sustainably, meaning from renewable electricity, or of course in the context of the solar fuels network, sunlight. Before I start introducing our first speaker, I would just like to take the opportunity for some advertisement, if that's not too outrageous, and show one slide of some other events that are coming up for the solar fuels community. The first one, in fact, is already next week. You should see the slide now. It's the Chemical Science Symposium 2021. So this means it's supported by the RSC, and it will be on biohybrid approaches to sustainable energy conversion. You can see quite an exciting lineup of speakers, and it's not too late to register, and it's very inexpensive. So if you're interested on this topic, please sign up and join us. And also there will be a lot of time for discussions. And last but not least, there's a similar event then the following year on biophotoelectrochemistry for fuel generation or chemical energy conversion. And we really hope that this will be in person in Cambridge. Okay, so I will close this slide, and if you have any questions, just drop me an email. Happy to answer any questions. So for this session, we have 30 minutes at the end for panel discussion. This means I suggest that all questions are being asked at the very end, unless there's a really pressing, urgent question for the speaker. And our first speaker is James Durant, professor at Imperial College and also Swansea University. It's a great pleasure, in fact, to introduce James. He has always been at the very forefront of solar fuels research globally and is really the leading figure, I would say, in the UK. He has many outstanding contributions. Scientifically, he really is pioneering the insights we gain from on charge transfer kinetics and also catalytic mechanisms, in particular using trained absorption spectroscopy. And I think a lot of the developments now rely on his insights from previous work. James always had many hats. He is also the founding director, in fact, of the Solar Fuels Network. So he deserves a lot of credit from the community. He's also the director of the Imperial Center for Processable Electronics, not plastic electronics anymore. And is really involved in many initiatives. And one other initiative is, in fact, Mission Innovation, Challenge 5 on sunlight conversion. And he will be talking about mission innovation today. So James, the floor is yours. We look forward to your presentation.
Thank you very much, Owen, for that kind introduction. And thank you, of course, also to all the organizers today. I'll share my slides. It's a great pleasure to have a chance to talk to you today. And of course, this is particularly timely given the build up towards COP26 in Glasgow later this year. So I'm going to be talking, first of all, more generally about the motivation for solar fuels and for solar-driven fuel synthesis. And then I'll focus on mission innovation. And as Owen mentioned, the recent roadmap, which was published by the Innovation Challenge 5, which is focused very much on the area of the solar fuels network on sunlight conversion. So when we think about how we can harness sunlight, and in particular when we think about how we can harness sunlight through electronic excitations, then of course there are 2 well-established pathways to do this. We have plants, which of course many billions of years ago evolved to harness sunlight through the process of photosynthesis to synthesize sugar. And this, of course, is a fantastic inspiration for my own research, but also for many of us around the world trying to understand how we can harness sunlight. More recently, of course, there's been a lot of work. Make this smaller. Oh. See, there's lots of pictures of people. Never mind. I'll just go back to where I was. There's a process of photovoltaics, which has become increasingly successful at turning sunlight into electrical current. And of course, you can't go far around the UK now without finding fields of solar cells. This is, of course, a fantastic success story. But what I want to particularly focus on this afternoon, and what is in general the focus of a solar fuels network, is a process of artificial photosynthesis, how we can harness sunlight in chemical systems to convert sunlight to fuel, or indeed to chemicals. The motivations for solar to fuels, or what is often called artificial photosynthesis, are particularly around our need to synthesize fuels. There are many applications where electrification has only limited applicability. So, of course, the challenge here is that there's great progress in the development of batteries, and electric cars are one of the success stories there. But batteries have a significantly lower energy density than liquid hydrocarbon fuels such as diesel or gasoline, which is just about acceptable for cars when you have your Teslas with its fancy batteries, but is more challenging, for example, if you want to fly or for long distance marine transport, or indeed if you want heat to heat our homes. And so thinking about how we can synthesize fuels and indeed chemicals sustainably without and in a carbon neutral fashion is key. And I say chemicals as well as fuels because, of course, the synthesis of ammonia or the chemical feedstocks used by our chemical industry currently all is based upon fossil fuels and results in CO2 emissions. And we need to get away from that. There's other motivations. We need to store solar energy, and particularly as we move towards more photovoltaics alongside wind, then we have issues of intermittency and the challenge of how we store energy interseasonally, and indeed how we can transport sustainable energy between regions of the planet with high solar flux, regions of the planet with high energy demand. This is a significant challenge, and not so easy to do with electrons, but much easier if we can store the energy in chemical bonds. The motivation here is very much around how we can shift towards a more sustainable energy system. And so it's the idea that we have some form of renewable power which feeds in the processes which allow us to synthesize energy-rich chemicals. Maybe the most famous of which is, of course, green hydrogen, which is, I think, becoming an increasing priority in the UK and indeed globally as an energy vector. But of course, one of the challenges with hydrogen is that it's only sustainable if it's synthesized in a sustainable way. And the key interest here is, can we harness sunlight to synthesize hydrogen from water? There are, of course, many pathways where we can think about how we can harness sunlight in order to generate fuels and chemicals. And I've illustrated a few examples here. This meeting and my talk, and indeed the Sunlight Conversion Innovation Challenge, is particularly around the more direct pathways of directly harnessing sunlight to drive interesting chemistry. And this is an area which is getting increasing attention around the globe. You can see some illustrations here of just some of the global centres and initiatives which are trying to explore this pathway. And some of these centres are really very substantial. So JCAP, for example, has had hundreds of millions of dollars addressing just this target. Plants, of course, are already remarkably efficient and capable of harnessing solar energy and storing the energy in chemical bonds. You can see some illustrations here of the molecular mechanisms inside these leaves which drive this chemistry. And on a molecular scale, plants are able to convert sunlight to fuel with efficiencies which are not so different to a silicon solar cell. But of course, as an organism, plants did not evolve only to convert sunlight to energy. They also have to cope with disease, they have to cope with droughts, they have to cope with reproduction, all these things, which means that typically plants and the efficiency of biomass conversion is significantly less than the underlying chemistry. And of course, that's one of the challenges with using biomass as an energy source, because it typically requires quite large areas of arable land in order to generate significant amounts of power. The interest we have in this meeting is to think about how we can develop chemical systems which can achieve the same thing. And there are many different pathways to achieve this, both in terms of material and device configuration. And you can see maybe the most obvious and established pathway is using photovoltaics to drive electric catalysis. And indeed, it's already possible now to synthesize green hydrogen from electrolyzers powered by solar cells. The challenge here, of course, is that currently this green hydrogen is more expensive than hydrogen synthesized from methane. And of course, one of our challenges is to reduce the cost of solar cells and electrolyzers. But there are many examples of where people try to integrate the processes of light absorption and chemistry. And you can see here examples of photoelectrodes, or where you have an electrode driving, in this case, water oxidation driven by sunlight. Or you can have, for example, particles which directly absorb sunlight and which generate electrons and holes, which can drive the same chemistry. These particles have the potential perhaps to be the cheapest pathway for harnessing sunlight to fuel, but also currently are the least efficient pathway because of the tendency within these particles is for the electrons and the holes simply recombine rather than driving the chemistry. And so the challenge here would be to try and get the efficiency up high enough that it starts to become reasonably competitive. Just as one example of where the state of the art is in technology. And so these are photocatalyst sheets based on those sort of particles developed by Professor Doman in Japan. They're based upon a strontium titanate particle covered in catalysts, which he's been able to screen print down very cheaply over large areas. So this is an example of 100-meter square photocatalyst sheet demonstration plant, splitting water into hydrogen and oxygen under sunlight. It's fantastic as a demonstration. It shows it works. It was working for 6 months, synthesizing hydrogen and oxygen and proved to be remarkably stable. But of course, currently, it's not yet efficient enough to be commercially viable. And the challenge is how we can achieve higher efficiencies. Now, there are many, many chemists and material scientists and physicists trying to work out how to enhance such efficiencies. And you can see some examples of different materials and device configurations people are trying to employ this. And indeed, for those of us who were at the Solar Fuels Network meeting this morning, you would have heard examples of metal oxides, of polymers and buried photovoltaic junctions, all of which people are researching both in the UK and globally to try to develop new technologies and devices which could drive the chemistry we're interested in. It's a fantastically vibrant and creative field at present. What I want to move on to now is mission innovation and specifically what's going on in this space. So mission innovation was established by the COP21 Paris Agreement to work alongside the climate negotiations to think about how technology could help drive forwards clean energy solutions, and particularly thinking about how to enhance intergovernmental cooperation to achieve this. It runs in a 5-year cycle. The first 5 years, it drove pretty much a doubling of member government investment in clean energy innovation. At least that's what the governments tell us. And it's focused on 8 innovation challenges, which I'll talk about just more in a second. More recently, this year, there's lined up with COP26, Mission Innovation 2.0 has been launched. It's going to have a slightly different focus, particularly on green power, zero emission shipping and clean hydrogen, alongside innovation platforms, and how the innovation channels fit in to this Mission Innovation 2.0 and how our particular interest in sunlight conversion fits into that is something which is still ongoing. So these are the innovation challenges which were identified under Mission Innovation. And these address some of the challenges which were felt to be particularly critical and important for international cooperation to move forwards the clean energy transition. This is IC5, converting sunlight, discovering affordable ways to convert sunlight into storable solar fuels. That's what I'll be talking about in the next few minutes. And of course, this lines up very nicely with some of the other innovation challenges, most obviously the hydrogen innovation challenge, but also clean energy materials and thinking and its analogies with sustainable biofuels. Looking for sunlight conversion challenge in particular, then it encompasses a slightly broader range of scope than the solar fuels network. So of course it includes photoelectrochemical and photocatalytic pathways. It also includes thermochemical pathways using concentrated sunlight. It includes photobiological and biohybrid approaches. And it's concerned not only with the development of new materials and devices such as catalysts and light absorbers, but also the design, engineering and demonstration of devices and systems. Photovoltaics, also electrolysis, is the obvious benchmark approach. And it has a number of targets, but one of the key things we need to think about is how scalable the technology is, because we're talking about, on a global scale, terawatts of sustainable power being needed in a not so distant future. So we have to think about earth abundant and non-toxic materials. We need to have a reasonable energy return on investment, on energy invested, and we need to think about the recyclability of our devices. But there was an action plan agreed, actually called the Cambridge Accord, which is rather nice. I'm sure Owen quite likes that title, which came out of a meeting indeed held in Cambridge a couple of years ago. And following on from that action plan, there's a roadmap which was launched a few months ago. And this roadmap came out of a series of national and international workshops and built upon some roadmaps developed around the world, and you can see two examples there. You can download the roadmap. I've put the link at the bottom here, and I'll just give one or two highlights or insights into what that roadmap is indicating. And so the roadmap looked not just at the science, but also the place of solar fuels in the wider energy transition. And so it considered, for example, particularly our commercial partners were thinking about the value chain. What is the motivation for sunlight conversion? If you want to drive reactions of sunlight, what is the real cost benefit analysis and why we would do that thing, and what would be plausible business cases? And then it looked at a range of different technology pathways, and it thought about what would be the material inputs, and of course, not just thinking about splitting quantity clean water into hydrogen and oxygen, but thinking about can we use sea or brackish water, and if we're going to be using CO2, where's the CO2 going to come from, and can we extract it from the air? And then thinking about the products coming out, and not just green hydrogen, but also ammonia, chemicals and materials. It considers a range of conversion technologies, and I've already discussed briefly what those are, and you can see nice pictures of all these different approaches going along here. And one of the interesting things about the roadmap was to try to compare these technologies side by side. I'm not going to go into all details. It's a 40-page document that you have to read in detail, but this is just some of the examples of the conclusions about roadmap. And so, for example, one of the major challenges is thinking about the stability of the devices which we're developing. It identified the particular areas where materials innovation and development is needed. It identified a lot around what are the enabling technologies, and very obviously, for example, the opportunities from artificial intelligence and computing. I like the inclusion of operando analyses, and of course the issues not just developing the science, but also doing the technical, economic and life cycle analysis. And it started to identify what could be considered key milestones to drive this field forwards. And you can see some examples of milestones there at the bottom. It was a multi-author document with inputs from around the globe. And so in some cases, we had to be relatively cautious of what we said to ensure that we had a full consensus. And so, but not always so many numbers on how many years it's going to take to produce one thing, because we didn't achieve consensus. But you can see some examples of here that we for example, the idea of demonstrating direct solar-driven hydrogen production, which is cost competitive with steam reforming alongside carbon capture and sequestration within 5 years. We went on to more detailed technological objectives, and you can see 2 examples there for photoelectrochemical and photocatalytic processes, giving you an indication of where we are at the TRL levels and the milestones which would be appropriate to achieve, and also the key challenges and the key enabling technologies. I won't go into all the details of those. You can also see that he considered the challenge of integration. There's a great deal of work going on, new materials and devices, rather less work at a system level. And of course, this system level work is the work which is going to need more commercial engagement. And that photocatalyst sheet plant I showed you an image of in Japan is a fantastic example of that. The intention of this roadmap is to provide a point of reference both for policymakers and the academics and commercial companies working in this field to help us come together to understand what the challenges are and to focus minds on how to achieve those challenges, and also to identify and highlight the opportunity which these technologies have to potentially contribute to our transition to a more sustainable energy future. The summary may be that most of the work which in this area is not yet at a commercial level. It's primarily at TR level 1 to 4, with prototypes being demonstrated in many places around the world. The academic research is accelerating, so there's been a 10-fold increase in research publications over the last 10 years, which of course is very exciting and reflects the degree of interest in this area. There remain key challenges around the cost, the performance, the durability, and the integration, and particularly how we can start to connect the science to industry. From an international perspective, then thinking about coordination and benchmarking is key, and understanding what standards there should be in this field in order for people to be able to fairly compare technologies across research groups and across countries. Going forwards, IC5 is now confirmed is going to become part of the Mission Innovation 2.0 innovation platform. How central a part and how major a part remains to be remains a point of discussion, and I do encourage everyone here today to help try and drive that forwards. There remains, of course, a lot of key scientific and technology challenges, but of course, I think many of us understand that whilst the urgency of a need to develop sustainable fuels and chemicals, as illustrated by some of the rather dramatic images around the planet of climate change, it really mandates us that we don't consider all the possible solutions in series, but in parallel. And I certainly am very excited about the potential for sunlight conversion to contribute towards our transition to a more sustainable energy future going forwards. With that, I think I should stop. I don't know how long I've been, but I think I've been probably getting on over time. Thank you very much for your attention.
Great, thanks a lot, James, for a great lecture and a brilliant overview. As we said before, we will just go on to the next lecture. And our second speaker of the session is Pau Farras from NUI Galway, where he is a professor, I believe, or if not, he will very soon be one, I'm sure. He really has an extensive background in solar fuels research. And for me, particularly inspiring was that he was one of the very first ones who really thought about solar chemicals in a broader context. And it's also notable that he takes a very holistic approach to energy conversion now. So he really now, I think, embraces many different approaches, especially when it comes to applied streams of research. And that's why we invited him to give a lecture here today. But many of his initiatives, he's also a real supporter of the research community. And I'm happy to be part of one of his networks where I can really say that he's a brilliant coordinator and really a excellent supporter of the field. So from his, just to mention a few of them, Solar 2Chem, huge project, Flow Photochem, SFI High Biosol, and C-Fuel are 5 projects he's coordinating or very heavily involved, and they're all won, I think, more than £1 million each project at least. So it really shows actually the weight of activities he's carrying. So the expectations are very high now, Power, and I'm sure you will do extremely well. So it's a real pleasure to have you. And today he will really only be presenting C-Fuel, which is already an operating activity. And we are looking forward to hearing what is going on.
Thank you, Erwin. It's a real pleasure for me to be presenting in this symposium. I've tried always to be part of the UK solar fuel symposiums, and it's been always very fun to engage with the UK community, even though the last 5 years I have changed the island and I'm now in Ireland. But I'm very happy to share basically the work that we are trying to do in C-Fuel. Basically, C-Fuel is an European project in which we are trying to demonstrate the production of green hydrogen using solar energy and seawater. But as you'll see, we are doing a few tricks to make sure that we can do that at a pilot scale, not anymore in the lab. But before I go into the details, just after hearing James' talks, I wanted to talk a little bit about why do we think that we need to run in parallel basic lab research with innovation at a certain level. And this fits also with some of the roadmaps that James presented before. I like to have this analogy with the cars because at the end, one of the end uses of hydrogen is for mobility. So if you look at the first car prototypes that were developed in 1880s, we see that they are nothing compared to now, apart from having 4 wheels and some sort of an internal combustion motor, but that's it. It took about 30 to 40 years to go from the first prototypes into cars that were mass produced. And after 100 years, we are still developing cars. So basically innovation and research on part components, aerodynamics, etc., is what drives optimization. And this is only for internal combustion engines. So imagine basically all the research and innovation that needs to be put into electric cars and fuel cell cars. Yeah, so just wanted to mention that to make sure that any new technology that is being developed in the lab now can have some sort of a complementary technology that can be extrapolated at a larger scale so that we can have a faster impact while we are still developing the new technologies. So going back to the project, so C-Fuel is an Interreg Atlantic area project. It means that basically we are covering most of the regions in Europe that are basically touching the Atlantic Ocean. C-Fuel has partners from the quadruple helix, so it means that we have partners from academia, from industry, from the civil society, and also from public and non-profit organizations. We started the project with about 11 partners, and we are now 18, with some additions in the last 2-3 years of partners that at the beginning of the project we didn't even dream about. Okay, so as you can see here, we have partners from the UK, Ireland, Portugal, and Spain. And apart from the academic partners with my colleague Alex Cowan in Liverpool, we have also some major industries that are involved in the project now. So to have a bit on a background for C-Fuel, I just wanted to mention some of the challenges that exist in the Atlantic area regions and are common in most of them. So most of the regions have isolated territories, and the most highlighted ones would be most probably the Canary Islands, Azores, and Madeira. So these are islands or archipelagos in the middle of the ocean. They are not connected to anywhere. They have a large energy dependency, and because they don't have fossil fuel resources, the imports for energy, for heating and for mobility are extremely expensive. At the same time, these locations, you don't need very big installations to cope, to meet basically the climate target demands of going to renewables, because there is not much population, there is not much industrialization. So there is some merits into going into the technologies that are aiming at not very large scale, but small or medium scale installations. And also, of course, the common goal that basically all these have very good connections. And I have some examples here of some of these issues. So, for example, in the Aran Islands, which are 3 small islands off the coast in Galway, a few years ago, the only cable that was connecting mainland island with the islands broke down. It was down for a few weeks. So basically, the population in the Aran Islands was without electricity for 4 days until they were able to get some generator in the island. And so what we are trying to see is how can, with the natural resources that most of these places have, how can we help them become sustainable? In terms of the energy imports, so this is a very rough scheme of the energy balance in the Canary Islands, and you can see that most of the income is coming from gas or oil that has been imported, which represents then a huge cost for the population or for the government to import really these fuels. On the other side, which are the opportunities that we have? So, as I said, islands have these challenges, but also they are excellent testing locations because, as I said, they are less industrialized, so the energy requirements are much lower. But also in most cases, they have excellent renewable energy potentials. So in the case of the Aran Islands, for example, here in Ireland, there is one of the best resources on offshore wind or wind in general, whereas in our partners in Portugal and Spain, they have absolutely excellent resources for solar energy. In terms of testing beds, so for example, this is an example of one of the islands in Madeira, Porto Santo, which was one of the first locations in which like a significant fleet of electric vehicles was tested using the renewable resources that they have based on solar and wind on the island. And closer to most of you, you might know the example of Orkney Islands, which basically have enough wind power that they become renewable completely. And the problem that they have is that basically they produce too much green energy and they need somehow a way to export it. And hydrogen is where this comes into place for this situation. So for fuel, we have basically 3 different objectives: the technical, the techno-economical, and the societal. On the technical, we have a pilot plan that will be installed in the Canary Islands. We will have some cars that are now using diesel, and they will be replaced by cars that will be using hydrogen. Then more on the basic side of research, we'll be looking at how an electrolyzer is operating under power intermittency, that's connected to the solar energy. And also how can we improve the materials that you have in electrolyzers to make use of another water source that is not competing with drinking water. In terms of the techno-economics, we have a business model that will be created based on the results of our pilot plan in the Canary Islands. And then we are conducting some studies in other locations of the partnership in Portugal and in Ireland to see how we can mimic or we can replicate the study in the Canary Islands to other locations. In terms of the societal objectives, we believe that these become very important because when you look at islands, the communities in the islands are very close. So basically, the best way to implement new technologies in those locations is with engagement and support from the local and the regional stakeholders. And that's part of the work that we are doing. So in terms of the technical part of the project, so this is a very simple scheme of the installation. So we have a good number of photovoltaic solar panels, commercial ones, with also a few windmills that are connected to our electrolyzer, our hydrogen refueling station. These renewable sources also power the desalination plant that takes up water from the sea and converts it into potable water that is used at the installations. And also this potable water is then is used as input for the electrolyzer to produce green hydrogen. So we have also a few ones that I will show you in a few moments. So a summary. So basically the installations that we have with our partners in the Canary Islands, they have over 50 megawatts of renewables installed, mostly on solar panels, but also about 10 megawatts of wind energy. Our installation, our refueling station will be connected only to the solar panels. They have also 2 desalination plants that produce about 175 cubic meters of potable water per day. And our hydrogen refueling station will be producing about 12 kilos of hydrogen per day at 350 bar. Okay, so just by looking at the numbers, we see that in our case, we are using a very, very small fraction of the water that is coming out from the desalination plant. Okay, so basically, to produce about 12 kilos of hydrogen per day, we need just over 150 liters of potable water. So that's orders of magnitude much smaller than the actual production of the desalination plant. And also to produce this amount of hydrogen, we need about 75 at most kilowatt of renewables. Okay, so this is just really a small pilot plan to show that this is actually something feasible. And we are looking also as well how to scale up this into a pilot plan that can become feasible in the near future. And of course, we have also a few of the bands. And the objective of this is to show that we can use this green hydrogen for supporting green mobility within the partners that we have in the Canary Islands. So looking at where the pilot is located, okay, so these are the installations of our partners in Tenerife, and you can see a good number of the photovoltaics that are located in the installation and some of the wind turbines that are also in the same location. And this is basically where the hydrogen filling station will be located in the next 2 weeks. So we are expecting to have completion of the pilot plan and operation between mid to end October. On the 3rd of November, we will have a public launch event with authorities from the Canary Islands and from the funding program as well. And by the end of January 2022, we expect the finalization of the first stage of CFuel. And we are working on extending this further to conduct more tests and more innovation into this project. So just a few technical things about the refueling station. So this is how it looks like. It is built by our partner in Scotland, in Edinburgh, Logan Energy. The hydrogen filling station has the capacity of 12 kilograms of hydrogen per day and is using a PEM electrolyzer. So it's a commercial electrolyzer that is located in this box, let's say, which has also a hydrogen storage of about 40 kilograms of hydrogen. So looking at the container, so this is basically all the components that you need for a hydrogen filling station. The only input that you need for this is a supply of water and electricity. And then the outcome would be the hydrogen at 350 bar, which can be used directly to refill the vans. And also some water that has not been used for the production of hydrogen. So this is a 40-foot container, which contains all the different things that you need. So the main core is the electrolyzer, of course, but also you need the compressor to get the hydrogen at the 350 bar that you need for the vans. So for the vans itself, when we started the project, since the Canary Islands are quite remote, but the thing that we saw is that basically there was no interest from car manufacturers to supply us with some of the fuel, like say fuel cell cars that were on the market. So we decided to convert some vans ourselves, and this work is done also by our partner Renewable Energy. So basically what we have done is we we took 4 Nissan EMBs, electric cars, electric vans, and we have added a hydrogen tank and a fuel cell into the car so that we can extend the range and the power of the van. Because one of the issues that we had with the Canary Islands is that some of the roads are quite bumpy and with uphills. So the performance of a pure electric van was not what we expect from a car or from a van. So the idea of adding this hydrogen fuel cell into the van is to have not only the range but also the power to really drive these vans into the uphill roads that you have in the Canary Islands, as you can have in other regions in the Atlantic area. In terms of the electrolyzer development, and this is the academic work that we are doing with the group in Liverpool, basically what we saw is that we could look at the different technologies that are existing now in terms of electrolysis and see which ones could be adapted to use water with less purity, like directly seawater electrolysis or wastewater electrolysis to produce hydrogen, so that basically you're not competing with the water needs with the drinking water, in particular for those regions that water is scarce. So some publications that appeared last year from our group, our colleagues in Liverpool, show that we can prepare some materials that are able to selectively produce hydrogen or oxidize water to oxygen, even in the presence of salts. And these are basically just alkalinized saline solutions that we can use directly to produce the oxygen with preventing any competing chloride evolution reaction. So in terms of the techno-economics, so we have done a few things, but I just wanted to highlight one that we think that is particularly interesting for the audience as well, is that we have done a map of all the islands, and all these dots that you can see here as hydrogen. All these are islands located in the Atlantic coast that we have taken a few parameters based on basically the resource that we have from Tenerife. And as you can see here, so we have taken some parameters and ranked them based on the readiness to implement hydrogen or to use hydrogen in those places to make them self-sustainable and help them the translation to a renewable society. So for example, here we can see the one from Tenerife, and we can see that the level of hydrogen readiness in Tenerife scores very highly. Okay, so it's about 66 out of 70. And this number is coming from these different parameters: the energy resource, availability of solar energy or wind energy, which constraints are there, which environmental amenities, the water supplies, etc., etc. Okay, so based on these numbers, what we have done is run all the islands in the Atlantic coast with their potential readiness to implement hydrogen in those regions. One of the, of course, issues that we have in, with every new technology is that to implement technologies at large scale, you need policy support and a policy framework. And that's a little bit related also to what James was talking about with the mission innovation. So what we have done is we have basically from last year the hydrogen strategy at the European level. Some of the European countries have published their own national strategies, and the UK, it was just published 2 weeks ago. But one of the issues that we have seen in particular for our project is that they are strategies based on large populations with a lot of renewable constraints. And what we see is that in our case, for island regions, there are no specific strategies to implement green hydrogen in those regions. So what we are doing is basically working with our partners in the different regions of the Atlantic area to develop roadmaps and further on to develop sustainable energy action plans that can be used for those regions, for these island regions, to have a more detailed, a more specialized roadmap for implementing green hydrogen in those islands that is more adjusted to the needs of those islands. In terms of the societal impact, what we have done, sorry for a lot of text, but basically what we have done is engage with different stakeholders in the island of Tenerife. And in our case, what we have seen is that for these island communities, in particular, in our case for Tenerife, about 75% of the economy is coming from the touristic sector. So what we are doing is using the touristic sector in those surveys to gauge which would be the interest of basically paying off infrastructure for these new technologies based on the income coming from the touristic sector. And in particular, talking about the work that we are doing in fuel and green mobility, what we are mainly aiming at is to engage, and we have engaged already with rental companies in the Canary Islands to see if they would be happy to have a line within their rental cars that is based on fuel cell, hydrogen. And also see if tourists that are going to Tenerife would be willing to use these fuel cell cars if the infrastructure is in place, and even how much would be willing to pay extra to test a hydrogen car instead of renting an electric or a diesel or petrol car. So we have done this with different stakeholders, with car manufacturers, with car rental companies, with even tourists that we have taken in the Canary Islands. And this is now getting into the next stage, which would be once we have the hydrogen in place at the end of October and November, we will start also new sets of surveys with tourists in which we will allow them to do a test drive of the car and see how they have changed their perception of the car after the test drive. Yeah, so this study it hasn't been done anywhere in the world yet, so it will be unique. And it will allow us to have to gauge which will be the interest of really applying this type of policy incentives into island regions in the Atlantic to implement this type of technologies to help them to meet the climate targets. With this, we had the luck in the last 2 years to engage with both Toyota and Hyundai. And we will have Hyundai Nexo and Toyota Mirai available to run these surveys. And also for anyone that would like to see how it feels to drive a hydrogen car, you will be more than welcome to engage and participate if you want to go to the Canary Islands. So just to finish, and basically looking at also more like public engagement activities that we are doing, we have developed, and that's basically some job that is being developed with the Energy Agency in Tenerife, is 2 escape rooms, virtual escape rooms that are designed for elementary and from elementary to high school students to basically explain which are the advantages and also the challenges that hydrogen has and how this can be used to move into a more sustainable mobility. So far, it's only in Spanish, but we are working on the English version as well. And all this can be found in our website. With that, I'll just want to thank you, the organizing committee, for inviting me to attend, and also all the attendants for being here today. And just with all the different social media channels that we have, you are welcome to join and follow us. So thank you.
Thanks a lot, Pau, for this very clear lecture about this fantastic initiative. I really wish you and your team all the best of success. I'm looking forward to the discussion afterwards. So with this, we come to the final speaker before the panel discussion. And it's my pleasure to introduce Bert Wekhuizen. Bert is a distinguished university professor at Utrecht University. His background is not traditional solar fuels. I would say he really is an expert and a leader in material science, the development of in situ characterization techniques to look at heterogeneous catalysis. So it's certainly an extremely important expertise we urgently need in the field. So we are very much looking forward to your view on the topic. And I'm also excited because he published some recent works on or perspectives on plastics recycling, as well as, again, giving the field a much broader perspective also, I think, which is really useful to think beyond water splitting and some core reactions. With this, he has a very large activity at Utrecht, a very strong track record, also in coordinating substantial consortia. And with this being said, he will today talk about Synergy, and we're looking forward to your presentation.
Thank you very much for the kind introduction. You can hear me well? Just
yes. Yep.
Yes, perfect. Thank you very much. So thank you very much for inviting me and also being part of this 9th UK Solar Fuel Network meeting. I must say I also enjoyed listening to the previous 2 talks, because they also already set the scene, and forgive me that maybe some of the slides, of course, already are dealing with the topic, and that is, of course, unavoidable when you talk about initiatives within Europe to facilitate this transition. So I have the title, Using the Sun and its Energy to Fuel a Circular Society. I think that there are many things we have to do, and that is also including chemical recycling of plastics. But today I will talk mainly about what we can do with sun, what we can do with its electricity or its energy, and how we can also move it forward by organizing initiatives across Europe or even within the world in more general. So this is a slide which actually I took from one of my colleagues, Jens Norskov. And on the left, you can see the atmospheric CO2 concentration. On the right, the global temperature change. I think these kind of slides you have most probably seen in the past, but I think it all shows that we are now really in need. There's an urgency, and the latest, I would say, weather things. Well, for example, my native country is Belgium. There was a lot of rainfall in the past summer. It shows that we have to do something, and that these kind of heavy rains or things which are, let's say, not as usual as we are, or things which are rather unusual to us, we will have to fix it, because they are related to, most probably, to climate change. This is a picture which I took some years ago. It's actually when I was making a family visit, and we were in California. It's LA, and you can see it in summertime how it is. And I'm quite sure that many of our cities, when it's very sunny for a long period, you can see these kind of pictures where you see things where we will have to get rid of smog. I'm now in my early 50s, and I'm raised with images of acid rain. But also you can see, and that is the real why I have this back mirror, and we have solar panels now on the left. What I feel is, first, we solved issues in the past. I don't think my children talk about acid rain at all. They are not even aware it existed. But we also have to be aware that this requires effort, not only effort from science and technology, but also from policy makers. Also, we will have to convince industry to move forward. So it's really public-private consortia, European, worldwide efforts, which makes that you can move forward and solve real big issues like acid rain, but now also this kind of climate change. And it means that we will have to fuel in a different way. We have to move away from fossil resources, natural gas, coal, as well as crude oil, a situation on the left. But I also learned that we have to be aware that most probably we will not change that much our portfolio of products. Therefore, on the right of both left and right, you see almost the same products. They will change a bit, but not that much. Consumers really love luxury and so on. We can, of course, change a bit our behavior, but not that much. So we will have to make sure that somehow we are making the refinery of the future. And that will be based on renewable resources, renewable energy, solar, wind, and so on. I have another picture. Actually, I have a postdoctoral fellow who is very much engaged in design thinking. And I just challenged him by saying, well, what would be it looking like? Now, if you start to calculate that, It means that we will have to make enormous progress in making our energy and materials, chemicals, refinery, all these things we will have to make more efficient. Here I show you what the size would be if you would make a current oil refinery of only 1/3 of the current size. Have a look how many windmills. Have a look how many solar panels. Have a look also, because what you see here are CO2 capturing units. Have a look how this would look like. It means science, technology has to develop. This, of course, still regarding what is it, electrocatalysis, photochemistry. No, I'm not selecting a tool. I only state what would it bring, what would it need for CO2, for electricity or energy input. So we need disruptive technologies. Disruptive technologies where we as Sunergy, I will introduce later on what Sunergy, where it comes from, actually from 2 initiatives before. So we want to use renewable energy, CO2, water, nitrogen, and so on. And we want to make sustainable fuels and chemicals. We want to store them, produce them, and develop technologies. We want to cover different TRL levels. That means we will have to work together with academia, institutions, but also with government and industry. We focus on renewable power conversion and fuels and chemicals, electrochemical, thermochemical, photoelectrochemical approaches, things what has already been discussed by my colleague Duran, but also by my colleague Costa. 3 key reactions we want to focus: water splitting, CO2 reduction, nitrogen reduction, of course, all what is makes and also its derivatives, because you want to make also the compounds out of them. Science has to develop, scale up has to be realized. This is not something what you do in one single lab. It's not what you do in one industry, but also not in one country. Sunergy originates from 2 flagships, Sunrise and Energy X. And we started to discuss March 2019, how we would develop, unite our forces. In my opinion, there is not yet a clear winner in technology or science. It is, I'm coming from heterogeneous catalysis, as rightly pointed out by Erwin, but homogeneous catalysis, photocatalysis, electrocatalysis, biocatalysis, each of these have to be developed. Most probably, it depends on which country, which technology will be prevailing over the other. Are we really making the one refinery of the future? Or do we have more dispersed refinery of the futures? And are they different in, let's say, Saudi Arabia compared to UK or the Netherlands? So we have been merging our 2 initiatives at the European Conference on Catalysis in August 2019. And then I have to say that as everyone has experienced the COVID corona, we had a lot of initiatives or ambitions, but also I have to be fair that due to this corona pandemic, a lot of what we wanted to do did not really fly to its full extent. We were very lucky that just before the lockdown, we were in Brussels and we actually have made a formal launch of Sunergy. And we are now working to unite the roadmaps, which both initiative has developed, and you can find them on our website for inspiration. And we are currently seeing how we can now develop a new document, an inspirational document which brings together different initiatives. We want to go for overarching themes, new catalyst processes, heterogeneous, homogeneous, bioenzymatic, and so on. Different length scales of importance. Actually, you have not just a chemical or biochemical or photochemical issue, if you really want to scale and meet the terawatt and whatever challenge, you will also have to make sure that you have engineering approach and materials engineering approaches there. And it also require proper stakeholders engagement. If you want to discover new catalysts and processes, we will have to do it in our current way of doing. But that is not only helpful, we also will have to use AI. It's very popular, I have to admit. But I also believe that we will have to see how we can link all our failures together. We only discuss our successes, but from what is not working well, we also can learn. So can we find that new type of bringing together all these databases, all these the open science way of working, we also have to foster. Scale up, it means we'll have to work together with industry, but it will be essential. I heard already in the previous talk, sea fuel and also what is there happening. It shows that we will have, by trial and error, really by not just using normal water, but seawater, or by really checking what impurities are. For example, we work together with the steel industry, CO2. Well, it's not just CO2, it's CO, but also other metals and whatever which are there. So we will have to scale up, find out stability and so on, all what it takes. European Green Deal is there. I think already much of this has been stated by my colleague Duran, but that is already that we really have to find out how we can embed now these ambitions in the new Horizon Europe initiative and how we can see this. So one of the things is affordability of renewable energy. Yes, we have solar panels. Yes, we have windmills. But I also hope that a pictorial representation of this refinery of the future, whatever it may look like, shows also the scale. The scale is enormous. The scale means that a lot of capital has to be there. And I'm just also wondering what all the intermediate steps will be towards 2030 and 2050. The right-hand image has been shown by James Durant, because you can see the batteries in the left corner. And yes, we want to make liquid fuels. Yes, we want to see how we can develop them. And we also want to see what the future is of hydrogen. In the Netherlands, we have now a new initiative, large initiative from the government, which is on producing hydrogen, using hydrogen. Can we mix it into the natural gas grid and whatever? But also can we make other steps towards other fuels and so on. It means it's not just chemistry. It is steel, cement, mobility, and so on. It's whole materials and energy infrastructure. I often show an example from Welte, Germany. I had a chance to visit it. It's not so far from Bremen. There they have a biocatalysis, which makes biogas, methane, but also CO2. And there's also water electrolysis done by renewable energy, windmills, and so on. And together, you can actually convert and do CO2 methanation and make methane, which you can inject in the natural gas grid, which is then an e-gas. But that middle part here, which I show here, it's classical technology. It's the Sabatier reaction of 100 years ago with a nickel-based catalyst, which we all know as a Sabatier type catalyst for doing hydrogenation catalyst. But can we do more than that? Can we make diesel? Can we make gasoline? Or better, maybe not diesel and gasoline, but can we make the fuels of the future which are used for whatever? Can we make our building blocks for chemical industry and so on? This panel was here something what we put in front of our building, and we are working on electrodes. Yeah, of course you can use platinum or whatever, but can we make it from alternative metals, which are less scarce and less, or are cheaper, less precious? But then the whole thing is on stability. One of the things which will be very important in the future is, if you make new materials, are they really durable? Can they really maintain for a while their function? And also, can we make sure, because I show you here in left top, this hydrogen oxygen, can we change, for example, the oxygen reaction and go for other type of electrolysis or photoelectrolysis or photochemistry reactions? So if the refiner of the future is there, do we not have then to consider right away chemical recycling of plastics or recycling of materials? Or better, can we not right away introduce circularity aspects? Circularity of elements, not only of carbon and nitrogen, but almost all of our elements. That is important. That will be the way to create impact. That is where we want to stand for, disruptive technologies. How? By bringing together people, by finding opportunities together with European industry, by creating leverage across Europe, coordinate actions, reach out to Brussels, and try to find common sense, but also common ground. And by doing that, we hope we can impact people's life and also change it. But it will be done by a push-pull mechanism. On the right, you can see a figure which we often use in this consortium because it shows the research portfolio and the technology portfolio. It will be a kind of ping pong, where from the scientific progress and the technology progress, you will have to see how scientific breakthroughs can progress. And that means you have to do that via interaction with different stakeholders, industry as well. That means this multi-pronged attack to the problem will lead to options. Options where we not yet know which will be the winner. The winner will be maybe only determined in the course towards 2050. No matter what the winner is, we will have to inspire each other. And therefore we have to coordinate and go to these major initiatives, because they will give inspiration, but also bring together communities which do not speak or speak not too often or not enough. Engaging startups in chemical recycling, and therefore I'm glad that Erwin mentioned that. Yes, we have big companies, but also we have a lot of startups where new low TRL level type of approaches are explored. At the same here with hydrogen, CO2, whatever. There's more than the big petrochemical industries. We want to do that and see. We are currently working on the ramp up phase towards a large scale R&I innovation, research and innovation initiative. We are fostering, we are helping, we are providing support letters, and we want to be glue or a connector between different initiatives. So for people who want to have our support, more than welcome. We also are working on a CSA coordination action where the deadline is at the end of this month. And several of you or even partners linked to your initiative or your community are participating. So what we want is we want to see how within the whole landscape of Horizon Europe, we can see how different initiatives which are of importance to us can be created. And very specific is that we are currently working on CSA towards this large R&I initiative with different work packages, which I show here on the slide. Too much to dwell, but of course, if you're of interest, you can always email us. And we are doing it for the community. We're not doing it for us. We are not doing it for Utrecht University. We are doing it for the whole community. So I'm doing the coordination together with Frédéric Chandezon. We have an industry board, which is chaired by Maximilian Fleischer from Siemens. We have an advocacy working group and so on and so on. We are organizing events, national workshop, industry, webinars, and we hope, I really hope, that we can do also a physical event, maybe at the end of this year or early next year. And I think it's really time now to meet again and to get inspirational discussions, and also people, young generation as well, to connect. So if you want to connect to us, you can subscribe to our newsletter. You can follow us on different media. You can just send us an email for contact. And of course, we are helping you, but also you can help us with support letters. So with this, I would like to give back the word to Erwin, and I'm of course glad to start a discussion with all of you.
Great, thanks a lot, Bert, for this wider perspective, and this gave us a lot of food for thought. And I really wish Synergy all the best in the next step of development. It's a great, and I think a unique possibility at the European level. So also thanks, of course, to all previous speakers. My job is now to hand back to Seb, I think, to collect questions for the panel discussion.
Yeah, sure. So if you have any questions, as I said before, please either raise your hand or use the Q&A function at the bottom. I'll open this as well here. And I guess we're going to start off with Irvin, who has raised his hands. Please, Irvin.
Yeah, I have first a question for Pau, in fact. So I found the idea of having car rental with hydrogen a really good one. I can really see that actually the tourists would pick that up. And then, of course, also if they have a good experience, that are more likely to buy a hydrogen vehicle afterwards. And I can also see them willing to pay a bit for the extra holiday experience. I would pay extra for sure. So maybe I get an invitation to the Canary Islands in the near future. But my question is actually really connected to solar energy use, maybe at the Canary Islands in particular. So I've just Googled the population density of the islands, and they're about 3 times higher than mainland Spain. And then also I can see that probably the tourist industry is not keen to cover all the nice scenery with solar panels. So how do you, I mean, I completely understand the view of energy autonomy, etc. But how realistic is it really, again, just in terms of land use, to have a significant contribution coming from sunlight at a touristic island like Canary Islands?
In the case of the Canary Islands, so you have the archipelago with different islands, and even one of them is already 100% renewable. So I think that what we really need to see is the combination of the land space that you have, plus the potential for offshore installations. And I'm not just talking about the offshore wind, but also the floating offshore solar panels that are now getting into the markets. And with this, at the end, if you have a floating platform that is close enough to the shore, then all the problems of renewable energy are almost solved. Okay, so at the end, what we are suggesting is that for those islands, with the resources that they have, not only on land but also off the shore, they should become, or they could become, renewable. And then it is just a matter of looking at which fuel or which chemicals are needed for those islands. And in particular, we are looking at for the mobility in this case.
Thank you.
Yeah, so a question around blue hydrogen. What does a panel think about blue hydrogen? And is it useful to sort of bridge the gap until we have green hydrogen at scale?
If I may answer, I think that the question will be, what is the transition? The whole thing about it. So you will have to have something at scale and economically viable. So maybe we can have something as like something on the horizon. This is where we want to go. And that technology has still to develop further. But in the meantime, we will have to make intermediate steps So I feel that we should do any effort to see if we can have less coal, or everything what is producing less CO2 is valuable, but we should be you should be careful that you don't be too slow, but you have also to make sure that you're making realistic steps forward. And that is the whole issue, I think. And therefore, I'm in favor of everything what is, if hydrogen is something where we feel we should invest and go for, then I would say then you use the infrastructure and build the infrastructure on your way towards that goal. And then it does not matter what the color is of hydrogen, to say it, with the exception of coal and whatever, to say that frankly on that. Yeah. But that is not blue hydrogen.
Okay, thanks. James?
Yes, clearly there have been some reports recently about, certainly in the UK, about concerns about the real impact of blue hydrogen on climate change. And I think those we do have concerns we do have to take seriously. At the same time, I'm aware that there's a huge amount of investment in the infrastructure of our energy system. And as we want to drive change, we need to think about where it's most important to invest in new infrastructure and where it's most important to use what's already there. And I think some of what Bert was showing earlier, where the idea that we can have chemical refineries which still produce the same chemicals and do some of the same processes, but where the energy inputs are different. Where we can use blue hydrogen as a way to facilitate the change in our energy system, as long as it doesn't embed us and lock us into a process which ends up not being so CO2 beneficial, then I can see some advantage. But I have some concern that the current government, UK government, focus on blue hydrogen may end up locking us into a process which may not contribute so much to helping us with climate change.
Thanks, Shane. Yeah, maybe we go with Alex first then.
Can the panel see any situation in the future where the CO2 emitters from industry actually become valuable resources? Because you've all made a point of stating that society is unlikely to change the products it uses and that the consumer likes certain products, and many of these are carbon-based, and we're going to need sources for carbon in the future. Do you think these are likely to come from these existing heavy industries, and could that actually become a valuable resource almost?
May I? I don't know. I will tell me my view first. Okay, and it's not for the people here in the audience, not surprise. I think it is very important that we, outside our own bubble, we talk about that a carbon-free society does not exist because we are built from carbon, amongst other elements. So that is the first thing. So CO2 will always be around. Second, it would be good if also the cement, the steel and other industries try to see if they can reduce their carbon footprint. But regardless, carbon is still added to it as well. So there will be always carbon there as well. So there will be CO2. We work together with CO2 emitter in the Netherlands. You can estimate who. And there we are seeing how they can get their CO2 use as a resource. The CO2, I believe, can be indeed used for more things than only going to a greenhouse to get it there for plant growth. Because that's, of course, nice as a, but that is not a scale where we're talking about. So I think the whole point will be, can we get the scale of the different industries in balance? Can we make sure that the input we have currently from all the oil tankers and whatever in balance? One, with all our large scale production units. And second, can we develop 400 ppm adsorption and further on. So these two things have to go parallel. It's my view.
If maybe I could add to that, then Bert, you talked about how it's one of the key science challenges now is CO2 conversion, and absolutely I agree. At the same time, I think sometimes it's not emphasized enough that if we can make green hydrogen, then the first thing we do is displace brown hydrogen. And that is the most obvious thing to be doing, and that technologically that should be our priority. Going beyond that, you're absolutely right that we're going to very likely need molecules of carbon in synthesized at very large scale. If we want to move sustainable power or energy around the world, we're probably not going to be shipping hydrogen. And we're probably going to be needing to store that energy either in ammonia or in hydrocarbons. And that's going to need conversion, and that's going to need, if it's hydrocarbons, it's CO2. And taking CO2 out of the atmosphere is, of course, scalable, but costs energy. And whilst we have plants which are producing high concentration outputs of CO2, as long as it doesn't have too many other chemical contaminants which make its use difficult catalytically, then it makes sense, and it also enables us to have, as you talked about, Bert, that we widen the stakeholders which we can work with to move things forwards.
Seb, can I add a comment as well? I'm not sure if I'm part of the panel discussion. Just on the question of if companies see CO2 as actually something useful. So it reminds me of a conversation I had with a bioethanol company. And in fact, I talked to them more as a challenge, just to see how they actually critically see the work I'm doing, actually, to be specific. But actually, they were extremely open, and they were looking for some utilization for the CO2, because they saw CO2 essentially as a pure stream that just emitting into the atmosphere without making any money. And maybe the most mind-boggling is that this conversation happened more than 10 years ago already. So this was the largest bioethanol company in Brazil at that time. And so I would say if some leading companies had that view 10 years ago, even much more so now. So I would really say approaching the companies, discussing this with them, I will see that most people would be surprised how open they are and how interested they are what can be done with the CO2. And of course, bioethanol fermentation is a great example, also as Bert showed. You could just use it for methylation, other chemistry. It's almost the best source of CO2 we have at the moment. It's concentrated and, well, not pure, but relatively pure, at least concentrated. Just one quick comment on the blue hydrogen. I posted a recent life cycle analysis of blue hydrogen versus gray hydrogen. And the conclusion they came is that blue hydrogen is only marginally better than gray hydrogen when it comes to environmental impact, simply because you have so much methane leakage and CO2 leakage on the way that it's if you sum it all up over the life cycle, it's not the same, but it does not a significant, not a substantial improvement. My interpretation, of course, but that's also what I want to hear. I think it argues very strongly for green hydrogen, and that blue hydrogen could be more a detour than really be really useful.
But if I may add, I agree. I did not read that paper, Evan, but one of the things we will have to work on is on methane combustion units to make sure that all the leak of methane is then converted to CO2 to get, well, you don't want to have the CO2, but because methane is more is a less good or a more greenhouse, I don't know how you say that, it's less good as greenhouse gas. So you want to get all the leakage away. So that is a challenge in its own right as well. So only then it will become something suitable as a transition energy or transition hydrogen.
I completely agree. I saw an interesting documentary very recently where people go with IR cameras and film the gas facilities and actually show all the leakage and post it online. So there's a lot of public pressure coming for the oil companies to really seal up the methane tanks.
Yes.
Yeah. Following up on the methane issue, here in Ireland, since the agriculture sector is so important, one of the more, almost the CO2 emission problem is almost as bad as the methane problem. And probably in other countries, like probably in the Netherlands, would be something similar. And the main problem with the methane is that, of course, it's not a centralized emission like with the CO2 that you have highly intensive CO2 emitters. With the methane, it is almost impossible to have really a concentrated source. So the only way probably to look at the methane problem would be really to develop, and that's part of the new technologies that probably we should look at, develop methane absorbers, not probably for the direct CO2 capture, but the direct methane capture from the atmosphere to try to solve these issues. And in terms of the CO2 conversion, I may add that also looking at these flagship projects that can be used also to move both the industry, private investment policies into the right direction. I think that one clear example would be the case of Iceland, for example, where they have like the biggest green methanol production plant that is based on using green hydrogen and transforming the CO2 into methane. And of course, they have the clear advantage that they have free energy there with the geothermal. But with the more increase of renewables in the different European countries and elsewhere, this could be something that could be extrapolated elsewhere when the price of renewables become at a certain price. So just that having these flagship projects and making sure that people are aware of those projects, I think that is very important.
Thanks, it's great. Paul, I've got a question for you actually, more specifically, I guess. Could you comment on sort of the risks of hydrogen and also the perceived risks of hydrogen? Do you have any experience in that sort of space? Because I mean, if I speak to, for example, my mom mentioned hydrogen, the first thing she would say, oh, that's dangerous. Can you comment on that, please?
Yeah, of course, this is a problem that we are facing. And when we started the project that like pre-COVID, that we could do live events and talking to the public, that was one of the main concerns. But at the end, I think it's just people getting normalized into what you have in the environment. If you go to the petrol station, you have petrol that is much more explosive than hydrogen. So it's just a matter of getting used to what you see in the normal. And that's why having those projects that you can see, like buses, trucks, cars running on the streets and there's nothing happening. That's what really would drive societal change as well.
And the Tesla cars also burn.
Thanks. Maybe just go to the Q&A section here. There's some questions from the audience as well. First question, I guess you sort of answered already, but I'm going to ask it anyways, is around sort of the different methods, of course, of making catalysts, sort of immobilized molecular catalysts or materials or enzymes and so on. Which do you think is the most promising out of these?
Well, my own field is heterogeneous catalysis, and James is photocatalysis. I just am now saying, so we can always advocate for our own field, but I think that's not wise. I stated something about what will be the scale of the operation and the engineering aspect. I want just to see, it's not my field, I'm just entering it. I'm only more recently working in photocatalysis as well. And one of the things where I find is there's a lot of possibilities if you think in devices, and I mean that was also what Paul was telling. So what is the device or the unit? Think about our solar panels at this moment. So the one I have on my roof, okay, produces electricity. Okay, but is that what you want? Okay, I can have a battery. Fine, but can we not think about communities? It was mentioned about farms. What about new way of think about a circular farm, where we think about energy integration, whatever. What about a chemical plant? Is it not time that we, and it will take time, 2050 or whatever, is it not time that we think about totally new way of how we connect everything? And in that case, I'm not sure that there will be always one winner or that technology will be the prevailing one. It will be a combination, most probably. Okay, I just throw it in to my colleagues and then we see, it's a panel discussion. So I just want to trigger you.
Well, thanks, Matt. I guess James will have to say a few things as well.
Yes, I guess I have 2 points there. So the original question was around materials and molecules and enzymes. And I guess one of the biggest challenges there is the distinction between stability and specificity. That when we for scalability and stability, then currently the heterogeneous materials are winning, both in electric catalysis and photoelectric catalysis, and maybe they will carry on winning. I have been struck with how rapidly the stability of molecular catalysts has advanced. And certainly for some more specific reactions, and maybe for some CO2 reactions or nitrogen reduction, then the ability to really tune the details of the catalytic function in a molecular structure, or indeed use an enzyme, has some advantages. And whilst I tended to assume that research on molecular catalysts was an interesting scientific study, but unlikely to be a technology, maybe I'm a little more open now. Coming back to what Bert was talking about in terms of how we can think about systems and how it all may come together, I have another hat in Swansea where I work with at the research centre, looking at our way to embed sustainable power into buildings and into communities. And I think one of the things which is worth thinking about going forwards is not just what makes the most economic sense, but what makes the most sense to how people and communities function. And if we are going to drive forwards a sustainable energy transition, people need to be with us, and we need to listen to what is going to make people's lives better and understand. And people can get empowered, just as Owen is talking about the idea of driving a hydrogen fuel cell car on holiday sounds a good idea, even if it costs you more money. And living in a house which is sustainable is something which people will pay money to do. And if we can harness that positivity, then that can help move things forward. So that requires us to think about different scales and what is appropriate at what scale, and how to integrate these systems, the new energy systems, in ways which people feel comfortable with.
If may add, I think that one of the most advantages of renewable energies is you always talk about distribution production, and I think that this links very well with community sense. And in our work with islands, not only with the Canary Islands, but in the other islands that we are working on, this is something that they really like, because island communities are very close. And if we can give them the option and show them solutions for them to become sustainable and not dependent on big electric companies, big oil companies for their mobility, for their heating the houses, for cooling the houses, I think that's the power of renewables that we can harness. In terms of the technologies, in my view, and following also some of the discussion, I think that with the Synergy's roadmap, it's clear that there will be complementary technologies that they need to evolve for different fuels and chemicals. And the good thing of mentioning fuels and chemicals is that you can put on the pot everything there. So we are talking here about the fuels that, of course, we'll need in large scale with hydrogen, the CO2 reduction products, but the same technologies can be applied for more specific transformations, as we have seen in recent reports in the literature, basically targeting specific reactions in the pharmaceutical industry using only solar energy could be very, very beneficial. And with that, you just need a small amount of material or the catalyst. So that's that complementarity that gives all these different options. That's something that we cannot lose in the community, I think.
And can I just add a comment to defend some of the biological catalysts? So I fully agree with the solid state materials and molecular. I really emphasize also what James said. I was also very surprised to see the advance of molecular catalysts, especially when they really integrated with solid state materials and how effective and stable they are. For enzymes, I think we discussed, also talking isolated proteins, catalytic proteins, enzymes, I think it's a very broad discussion, because on the one hand, and we use them ourselves in the lab now, for example, if we talk about biomass or waste conversion, there are many enzymes that are very useful, super cheap and super stable. One enzyme would be cellulase, right? The enzyme that breaks down cellulose. And we buy them at a cost of what, 1 to 10 pounds per kilogram, and they're super stable. So they're really useful for us to pre-treat our waste, which is then being used for solar conversion. But of course, on the other hand, if we talk about enzymes that are highly air sensitive, fragile, like hydrogenases that we also use to make hydrogen, in this case, I would argue they will not be commercially relevant. Maybe for sensing, but not really for fuel generation. So I think we really need to differentiate what type of enzyme. And I can think of a good range of enzymes that could really be extremely useful also for solar energy conversion. But bio also stretches, of course, to live cells, or really microorganisms. And with synthetic biology and also power works on this, you can really start engineering now your microbes to make specific chemicals. So when it really goes to CC bond formation and selective chemistry, then I think the still biology has the edge over heterogeneous systems. So long story short, I think it depends ultimately what you want to make. If you're really just in water splitting, then probably you don't need biology. But if you go to more complex chemistry, I think that biology is key.
Yeah, I would like to add that the Werther plant, which I showed, had this anaerobic digestion plant, which took actually the waste from the Bremen city. And then from that, you got methane, CO2, whatever. Now, you can think about many other enzymes it's not my field, biocatalytic systems in that anaerobic digestion, which would produce not the methane, well, maybe it will produce some CO2, but not produces methane, but other compounds. And then, the whole biotechnology will help a lot in designing that. So I'm repeating myself. I think we should also think about the whole circularity. What is now a wastewater treatment plant in a city? Should we not think differently about that? And then biocatalysis is key. And so Erwin, I agree with you. So I'm, of course, advocating for heterogeneous catalysis, and it will, at scale, it will have surely an advantage, as it has proven in chemical industry. The question will be is, do you need for everything the same scale, or is the heterogeneity in the feedstock an issue for the catalyst under development? If the feedstock is dirty, complex, and whatever, then maybe adaptability is key, and then certain things can be maybe more stable, as what James was saying. That, I mean, you need stable systems who can run for a while, and running for a while is not just days, but months, years.
Thanks. Got another question from the audience as well, from Salvador. He's asking on sort of precious, scarce metals that are currently required to develop and commercialize technologies. Can you comment on that? And I guess, like, how can we move away from this?
Yeah, I don't want to start always, so just someone else.
I mean, I think that's part of the innovation and the research that we have to do. In fact, if just looking at hydrogen production and PEM electrolysis, of course, if all the hydrogen that we need to displace the Greek hydrogen that we're using now is produced in PEM electrolysis, there is not enough iridium to power the current technology. So that's part of the innovation that we have to look at, and not only trying to replace the precious metals in PEM, but looking at other complementary electrolyzer technologies like the solid state, solid oxide, or the anion exchange electrolyzers that they don't require this type of precious metals. But I think, as I said at the beginning of the presentation, I think that we really need to drive this in parallel, innovation and basic research to improve these technologies while we start implementing them, because if not, we are late already to try to get to the climate change targets.
I agree completely, Pau. I would just add that it would seem we need to distinguish between the pathway from the end. If we look at how solar cells have developed, then thin film solar cells still use indium tin oxide as a substrate, and SiC solar cells are full of indium. If we look at the PEM electrolyzers, you say they have iridium in, and those have been and are very useful and effective pathways to establish and develop a technology. But of course, you were quite right that there's not enough iridium, there's not enough indium to take those to the terawatt scale. But once you've got to the gigawatt scale, then that provides some financial incentives to find the alternatives which get you to the terawatt scale. You can also look at not just entirely replacing an element, but reducing its content. And so I keep getting told by Evan Stevens how an interesting challenge is not to replace iridium, but to find how you can make electrolyzers with less iridium.
I also have one comment, maybe a note also for the younger the audience and the students. So when I started my group, I was very dogmatic that the group had to use water as a solvent and was not allowed to use precious metal unless really necessary, so except the ruthenium plus PP, which we couldn't avoid for a while. I'm saying this because I think starting a lab is a really great opportunity to really essentially set the scene and have this change in direction, which from experience now becomes much more difficult. But what I try to say is I was very dogmatic also, it had to be 3D transition metals, etc. But then again, it depends on how you collect sunlight. And what has been striking me the last few years is really concentrated solar light. Because if you look at the work by Sophia Hausner and others, if you really work at a couple of hundred suns, then of course also goes back to James actually, the amount of precious metal you need is decreased dramatically because you just concentrated on a very tiny area. And if you then even manage with a very low loading, then even probably we can even use precious metals. So, you know, 3,5 semiconductors with some iridium, platinum. Not saying everything can be made by it, but I can really see it to be a significant contributor as long as we don't need these massive areas and this very high loadings of catalysts. I think it depends really ultimately on the setup and configuration. But of course, if we can make cheap catalysts, we should make them.
Okay. I guess like sort of a question I asked myself as well, like what can I do as a private person to facilitate all this? Do you have any comments on that?
Oh. I can see that none of us are very keen to answer that. I'm aware that with lockdown, a lot of our lives have changed, and that's been some opportunity for reflection. I can imagine that as our lives reopen again, then we're probably not going to go back to exactly what we had before. And the old adage of think global but act local has some relevance. At the same time, it's important to recognize what can make a big difference and to use our own expertise as best we can to move things forwards and to remember the big picture.
I think that from my point of view, I think that with the work that we are doing, now it's particularly more important to make sure that the public knows what we are doing, which are the challenges and the opportunities of this area of research and innovation, because if new technologies that do not come out into the commercialization stage, then there will be no way that we can get to the climate change targets. So I think that, I mean, for me, working on these hydrogen projects, we have been in many events where people from companies are not aware of what is already on the market in terms of green hydrogen and the advantages that you can have. So I think having really these public events and making sure that you engage with industry stakeholders, with policymakers, with schools, I think that that's one of the most important things that we can do at the moment.
If I may add, I think what James tells is right. I think we have seen how the CO2 production decreased during COVID times. Of course, we also have to realize that we missed a lot. You can see that from everyone now enjoying a bit more life. But we also have, so I must say that talking with my children and trying to get them realizing, so they are the future generation. They will make actually the way they live and how they will cope with CO2, whatever. That means, what about food, meat? What about, so there are many things where we will have to think cautiously. I mean, of course, I also enjoy, I'm a flex eater, so I'm not very, but I think we should be more, I mean, COVID has, at least for me, I must realize sometimes I was like, why I'm flying back and forth between place A and B and going for a conference as a scientist. I miss conferences, let's be fair on that. So, but we also have to say that certain things we can do via this medium in the future. I'm quite sure that it is even more effective. We don't have to go every day to our work and sitting there for a long period in the car or whatever with traffic jams. But it will require that we will have to rethink and reflect, and also being able and willing to pay a price for it. Price also money-wise, monetary-wise, because do you find it normal that when I would go in the Netherlands, I'm here in the Utrecht, I would take the train back and forth to Amsterdam, which is not that far for people in the UK. I mean, come on, that is from not even Heathrow to London Center. That the price is higher for such a train ticket than flying to Turkey or whatever, or to the Balearic. That does make no sense at all. And that means that we have to get back to normal in that respect, because it's not normal. And I know, I mean, I should be careful because our railway system is still, I think, less expensive than yours. At least the last time I used it was not, I was wondered how expensive it was in the UK. Let's be fair on that. But I want to say with it is that it is that kind of, we should really try to rethink what we find as normal and abnormal, and what is then what we want to pay and how we educate the next generation. And if we take that into account, I think we can already save a lot of CO2 and a lot of energy. Of course, it starts with yourself. So I also have to admit, and many of us as professors, we have been big, at least I have been a big CO2 emitter in the past decade. And all of us most probably, because we travel and we do a lot of things. So it starts with ourselves. It starts in the supermarket when we buy things. It starts by making a careful choice. Do we want to have this or that? And so on. So it's that means we will have to this is not only about chemists and technology people. It will be also about people from other faculties, from psychology, from social sciences. We will have to invoke a lot of other scientists if we really want to make that transition. And that's far from trivial.
Very good point. I only have one addition. I think also being vocal, talking to friends, family, your community, I think is very important. The one thing I'm convinced is once the public really demands it and it becomes an election winner, the change will come very, very quickly. So I think it's once the population is behind the idea and is even willing to have a slight tax increase, or maybe it's not even necessary, it's just the will to do it, the politicians will take it in board and policy will follow very quickly.
You mentioned plastic waste. I mean,
yep.
The UK was even ahead of us, I mean, in all its public perception.
It's a fantastic example, yep.
I mean, come on, this was really, I mean, when I'm talking with my children, or we just go to grocery, have a look what you bring back from the grocery on a weekend day. I mean, and they say, Papa, Daddy, what is that all about? So, and that will change. They will, I'm quite sure it will bring a new way of living. And the only thing is, how fast can we do that? And and then I should keep my mouth. So, but we are in our bubble. We do not have to convince ourselves. That's easy. We also have a different salary scale. You also have to admit that. There are also people who are at another scale of salaries, and they're living, they're going to the cheap to Turkey or whatever country is their way to enjoy life, and you cannot forbid that. So we should be, I would say, that is the reason why I'm saying we have to invoke social sciences and other people, other disciplines to get that transition happening, because yeah, it's elitaric. I don't know. Yeah, elitarian. I don't know the English word for it. Okay, I think you understand.
Yeah, it was very nice to see actually on your Synergy slide, you had social justice there. And I absolutely agree. We need to take everyone on board.
Yeah.
All right. I guess that was a lot of food for thought, really. And I think we've got a little close here in the interest of time. Really want to thank the panelists and Irvin, for this event here. It was really fantastic discussions, and I really enjoyed the presentations, really sort of giving a backdrop to why we're doing all this. So yeah, thank you very much. And also want to mention that we have, of course, tomorrow the early career event. So if you're interested in that, please come along to that. We'll start tomorrow at 9:30. So with that, we'll come to a close here. And again, well, thanks very much for coming and participating.